Our project is the Biphasic Ionic liquid CO2 capture system. Our team consists of 4 chemical engineering members: Stephen George, Jeffrey Bartholomew's, Daniel Muskes, and myself, Berge Design. Each of us contribute to different aspects of the project, from process design to simulation and analysis. Carbon capture is all about removing carbon dioxide, or CO2, from industrial emissions before it reaches the atmosphere. This matters because CO2 is one of the main greenhouse gases driving climate change. Large-scale industries like power plants and chemical manufacturing release significant amounts of it, so capturing even a fraction can have a meaningful impact. For our project, we focus on capturing CO2 from a natural gas plant slipstream, specifically about 1% of the total exhaust flow, from a plant based in Arizona. While 1% might sound small, on an industrial scale, it still represents a substantial amount of carbon dioxide that can be intercepted and reused. Instead of treating CO2 as a waste, we designed a system that captures it and converts it into something valuable: ethanol. Methanol is an important industrial chemical. It is used as a fuel, a solvent, and a building block for many other products. So by converting CO2 into methanol, we're not only just reducing emissions, we are creating an economic value from which would otherwise be discarded. To design and simulate the system, we used Aspen Plus, which is a widely used chemical engineering tool. It allows us to model complex processes, explore different operating conditions, and predict performance, all without physically building the system.
A key part of our carbon capture system is the solvent we use to capture the CO2. Traditionally, carbon capture relies on a solvent called monoethanolamine, or MEA. MEA is well studied and widely used, but it has several significant drawbacks. In order to release the CO2 from the MEA, the solvent has to be regenerated at high temperatures, meaning the system consumes more power overall. It also tends to degrade and needs to be replaced over time, especially when exposed to contaminants in the gas stream, which increases maintenance and replacement costs. To address these challenges, our team explored an alternative solvent, an ionic liquid composed of dimethylaminopropylamine, triazole, polyethylene glycol dimethyl ether, or NHD, and water. This solvent was specifically selected for its enhanced CO2 absorption properties. Ionic liquids are unique because they can capture higher amounts of CO2 per unit volume than traditional solvents, and they require less energy to release this absorbed CO2 during regeneration. This has the potential to significantly reduce the overall energy used in a carbon capture system. To begin absorption, the solvent enters the top of a packed absorber column, while the flue gas enters through the bottom. The column uses Paul rings as packing, which are designed to maximize contact between the gas and liquid phases, increasing the efficiency of CO2 absorption. The combination of a high-performing solvent and efficient packing allows us to capture more CO2 with less solvent and less energy input. Another advantage of the ionic liquid is its stability. Unlike MEA, it is less prone to degradation over repeated absorption and regeneration cycles, which could extend operational lifetime and reduce costs over time. While the long-term performance of this solvent is still being studied, the initial findings are very promising and suggest that this approach could be a more efficient and sustainable option for carbon capture.
After CO2 is absorbed into the solvent, the next step is to release it so it can be used in downstream processes. This happens in a unit called a continuously stirred tank reactor, or CSTR. A CSTR is a reactor where fluid is continuously fed in and removed, while a mixer keeps everything well stirred. This constant mixing ensures that temperature and composition stay uniform throughout the entire reactor. We chose this design for a very specific reason. It helps prevent hotspots. Our solvent begins to degrade at around 400 Kelvin, so maintaining tight temperature control is critical. In reactors without strong mixing, you can get localized regions where the temperature is significantly higher than average, which can damage the solvent and reduce its effectiveness over time. The CSTR minimizes this risk by evenly distributing heat throughout the system. In addition, the continuous flow allows us to steadily process the solvent while giving enough time for the CO2 to separate. Heat is added to break the interaction between the CO2 and the solvent, and the mixing ensures that this process happens uniformly rather than in isolated regions. Overall, the CSTR provides a balance of efficiency, stability, and solvent protection. It allows us to regenerate the solvent for reuse while producing a concentrated stream of CO2 that can move on to the next stage.
After exiting the CSTR, the CO2 is compressed and fed into a catalyzed plug flow reactor, or PFR, where it reacts with hydrogen to form methanol on the surface of a copper zinc oxide alumina catalyst. In a plug flow reactor, reactants move continuously through a tubular system, allowing the reaction to progress along the reactor length. This configuration is well suited for gas phase reactions and can achieve high conversion efficiencies under appropriate temperature and pressure conditions. Looking at our results, we captured a significant fraction of the CO2 in the inlet stream, removing approximately 23 kmols per hour from the modeled slipstream. Of this, about 70% is converted to methanol in the PFR, producing roughly 13.4 kmols per hour. The crude methanol is then sent to a distillation column for purification, exiting at 11.56 kmols per hour at greater than 99% purity. These results demonstrate that even a 1% slipstream scale operation can reduce greenhouse gas emissions by an impressive 10,000 tons per year. From an economic standpoint, preliminary estimates indicate a capital cost of about $50 million and annual operating costs near $21 million. While high purity methanol can be sold across a range of prices, leading to annual income of about $15 million, the process is still not profitable due to significant ongoing expenses, including solvent replacement, heating requirements, and labor costs, which outweigh the revenue generated under standard bulk methanol market conditions. Potential pathways to improve profitability include upgrading the final product into a higher value specialty chemical, such as incorporating additives to produce chromatography grade reagents, as well as integrating heat recovery within the process.
Building on these results, several areas for future work emerge. First, we aim to better understand solvent degradation. Repeated thermal cycling and CO2 absorption-desorption can reduce performance and generate byproducts. So quantifying solvent lifetime and dominant degradation pathways is critical for predicting replacement or regeneration needs. Second, we would explore methods to remove degraded species and contaminants without large solvent losses. Targeted cleanup or reclaiming strategies would be essential to maintaining long-term efficiency while keeping operating costs manageable. Third, we would evaluate scaling beyond the current 1% slipstream design. Expanding toward full capacity would challenge flow handling, heat transfer, and equipment sizing, while testing economic viability. Finally, we would assess performance in a coal-based exhaust, where higher impurity levels provide a more rigorous test of solvent stability. Overall, this project demonstrates a pathway to both reduce emissions and convert them into valuable products, supporting a more sustainable and circular chemical industry.